of stuff. Okay, so we got two spherical asteroids or dwarf planets, whatever, but they're big enough to be pulled into space by their own gravitational. And assume there's no atmosphere involved. This one has mass M1, radius R1. This one has mass M2, radius R2. You stand on the surface and you shoot a gun straight away, straight up, straight away from the center. And it goes up to distance h1 from the center. So my question is, in terms of these symbols, what's the distance h2? In other words, if we know the two masses and two radii and how far the gun shoots here, how do we find how far the gun shoots over here? Okay. Okay, I think we've already done this, but let's make sure. You got two asteroids or dwarf planets, they're spherical, masses, radii, and this goes, you shoot a gun here, goes out this far. Okay, and this distance from the center is h1. Shoot the gun here, goes out this far, this distance is h2. So we want to find h2 in terms of the two masses, the two radii, and how far the gun goes here. Okay, same gun, which is key. Okay, so what we do? Well, we eventually got around to looking at the board we did last class and writing an expression here. Now, remember, I had the property to write PE, right? Identify, don't just write down a expression floating around on the board someplace. Identify it because that reminds you what it is. And when you look at it, you understand what it is. Also, write it down in a picture, okay? And be as specific as you can. So, you get this pretty obvious picture here. You got planet one implicitly because of the R1s and stuff. And you have the potential energies. And I'd probably be, what's the potential energy here? What's the potential energy here? What's the potential energy here at an arbitrary point, right? So with that, we were able to do this. That's what I give you I want to emphasize the advantage of having it all written down in one picture rather than here, there, and everywhere else, because you forget where to look. You even forget what you're looking for. Okay? Write down all the detail you can. You can write down the forces too. And you had no trouble doing that when you were prompted. Now it's M1, right? You have the M1 here and here. Over here, you get a little arrows with the M1. And it is an M1 that you're shooting. I didn't tell you that, did I? Okay. I didn't know that until it suddenly occurred to me. Okay. Once you got this picture, now another thing. Somebody wrote down this equal to this without these things in there. Okay, that was a really good start because you're saying, okay, the potential energies are going to be the same. Okay, well, they aren't. The changes in potential energy are going to be the same. I didn't prompt you on that. There's something missing there. Look at the picture, and you guys immediately figured out. Oh, yeah, it's the difference between here and here. Okay, because well, it is a fire from here, right? Okay. And you really can't fire anything from a point mass because R is 0 there, which means you have infinite gravitational force. You can't even get there. Okay. So these are point-like masses, and they do have a surface, and you got to be careful about that. Anyhow, that's good. There's an equation you can solve. Now, what principle did you use? Well, I said, well, you really want to identify why you're writing this stuff. It's because the changes in potential energy are the same. Intuitively, you understood that. And you're explaining, oh, well, there's no atmosphere, and there's this, there's that, and work energy theorem. You want to quote that work energy theorem to make sure you're on solid ground. Now, you're right, okay? And depending on how much explanation I ask for in a question, that might be a full credit answer. Well, the answer is then you solve for H2. But that's just simple algebra. Multiply through by all your denominators. Little messy, but it's not bad. But, I haven't seen any evidence anybody would have any trouble with that in algebra. Okay. So you go to the work energy theorem and you say, okay, well, you got the work by the non-conservative forces and then the change in kinetic and potential energy. And now that lack of atmosphere you're mumbling about tells you why you can toss this thing out, okay? It's 0. Because there are no, and you said it right, there are no non-conservative forces. So that gives you 0. And now you have this. Then you probably want to say same gun. Same bullet mass, and I never did specify that the bullets actually had the same mass. I give you different masses of bullet. Okay, but you're going to assume you get the same kinetic energy from the powder. Okay, it wouldn't really be true if you had different masses, but in the first approximation, would be pretty close. Okay, same gun, same bullet mass. We have the same initial kinetic energy, right? And final kinetic energy, 0 in both cases. Okay? Let's do a complete solution. You want to state all these things, and you really do want to state all these things for an engineer, so you don't miss something. And the bridge falls down, or your rocket blows up, or misses Mars, or crashes into Mars, whatever. Okay, these things happen. Don't know if we ever missed Mars, but we sure did crash into it once. Nobody wasn't careful with their units. $3 billion, no big deal. Okay, and loss of scientific information. Hopefully everybody learned a lesson from that one. That was back before you got to born. Unless you're a lot older than you look. Okay, final kinetic energy 0 in both, right? So change kinetic energy. And now everything's there. And you might want to have stated it in a more logical sequence. Once you get it all worked out and think through everything, you say, okay, now how am I going to write this out so somebody else can follow it? Okay. But there it is. And you saw most of that. But you didn't immediately think potential energy. I had to prompt on that. Even though I prompted you to look at that board and do it. Okay. Now, a couple other questions arise. Like, how much faster would the bullet have to be going to never come back? It's escape velocity. Okay. You're not going to be able to, you've got to move on to something else. What could you do with force? Okay, well, there's a question you ought to think about. You probably ought to go ahead and start the forces. The second planet. Okay. So the key is that a distance r, the force equals 3g big M little m. Some 2 in this case. Over R squared. Where R is the distance from the center. Work if you take the path from here to here, okay, then partition it. So you have R naught equal R2, right? And R sub n equal to H2. You have your typical ith interval. With its sample point. Then larger ith interval. You have your R I and your R I minus 1 and your R I star. And of course, you got your delta RI, which is just the RI minus 1, right? Then you see what your force is. Gravitational force sub I, if you wish. Is this, okay? Once you've got that, the work and I'll use the delta as a contribution of work on the ith interval. The work done by gravity, by this gravitational force, is the negative of your gravitational force times your displacement, which is in the opposite direction. That's why it's negative. Your force and your displacement are in opposite directions. And I don't have room to write out the sum and all that. Your work is going to be the integral from R2 to H2. Yeah, maybe right too small. Okay, big G, big M, little m. Over R squared. Negative. dr. Okay. Second way around here. Work equal integral from R1 to R2, sorry, to H2 of negative big G, big M, little m, over R squared dr. Okay, that's work done by your conservative force. Okay. Change of potential energy I defined in this course and have defined, hopefully you've thought about it, is equal and opposite to the work done by the conservative force. Okay. That's equal to the negative of your delta PE. And you can see that if you integrate this, you're going to get a negative 1 over R, which take care of that negative. It's going to be big Q, big M, little m over R, evaluated at H2. Okay. which will be this, but without the negative, because it's negative with the change in potential energy. And evaluated at R1 is this, but not the negative, right? And the negatives go in there because it's negative with the change in potential energy. You want to think about that in that connection. That's something you really want to understand. Okay? Well, now we're going to switch to simple harmonic motion for a few minutes. Got a mass M, net force negative kx. And we're switching gears, talking about simple harmonic motion. There's more to say about gravitation. We'll say it next week. But there's things that you want to get used to before we really dive into simple harmonic motion, before you get to the problem. So I'm going to give you 15-minute introduction here. You got a mass M, net force is negative kx, right? Okay. What's Newton's second law tell you about net force? Well, we'll talk because we're on tape here, but and actually, I'm going to cut this off, and I'll start over talking about it because I want to do it in a separate video. So we're going to